I would prefer to do that. Just
That beats two in a day.
it makes 2 in a week. I don't care. Let's just do it all in the same week.
How's it go, Kyle? Hey, something's going on with my video. Hold on. I'm gonna log back on in a second.
Sounds good.
All right, Kyle. Gotcha.
Perfect.
So let's aim for the 7th. Unless somebody's got like a real good reason, to not do that. Okay. All right. Oh,
Point the camera at.
Yeah.
I think it should be good to go, Kyle.
Good to rip. All right.
Yep. Everybody hear all that stuff? Yeah. Okay.
Okay.
You're
Cool.
good.
All right. Let's get going here. So just kind of recap where we've been and where we're headed. We went over, last Monday, we went over what the post-tension systems even look like, right? Bonded, tended, or unbonded, banded, uniform directions, just kind of anchorages, all that. Wednesday, we kind of went into stressing and some of the considerations around stressing, losses, more at the tendon level itself, anchorage zones, reinforcing at the anchorage zone. Then on Friday, we went into balanced load design using service level loads and the load balancing concept. Friday, we went over that again, and then we went into the strength level stuff. Then at the end, handed you guys that design example. And that design example, you could go through and you could look at. It's a very simple 3x3 bay concrete structure, and you could walk through design an individual bay. That's what it's doing. It's designing one of the center bays for post tensioning, doing all your drapes, and it's very in the weeds. The majority of what's happening in that design example, though, when it comes to the calculations, figuring out what those service stresses are and calculating your ultimate moments and everything there, that's all something that'll be done in your software. And so you just need to know how to do it once, and then past there, you just need to be able to validate the software every now and then, make sure it's doing its job correctly. So today, what we're going to start to focus on is all right, let's walk through, just like we would in the real world, how we're going to do one of these designs. I'm not going to get into the software because the software part is just a very, very small aspect of doing the actual design. A lot of it is the considerations that you as the engineer need to put towards the post-tension slab. And in general, in the industry, there's not a lot of great guidance of, hey, step 1, step 2, step 3, all the way through. So I put together this presentation of, here's 12 steps to kind of follow if you're to do a design. And these are the same exact 12 steps anybody in our office follows. I'm giving this exact presentation to the Structural Engineers Association of Colorado next week on, all very experienced engineers in Colorado on, here's 12 steps of being proficient in post-tension design, and here's some guidance on it. And then we're also going to give this to several other states as well. So this is very much tuned into what you would be doing in real world engineering on there. And the idea with these 12 steps is, one, to give you as the engineer confidence that you're doing it correctly and you're following industry standard approaches, and having reference material that you can always fall back onto if anybody calls you out thinking you're doing it incorrectly. So the first one's just to build confidence in you as an engineer as you're actually doing one of these designs. The second one is to become more efficient in the amount of man hours you spend doing the design. within structural engineering, budgets are tight. And so really what it comes down to is it's not, of course, it's life safety is always your number one priority, but it's really how many man hours do I have to design this and can I do in that many man hours to make money? Otherwise, we're losing money on the project. And following this approach makes it so that you're more efficient and it's less man hours spent on this particular task that you have at hand. What I've seen a lot with post-tension design, if you don't follow this approach and you just kind of go all over the place, it becomes very iterative and it's very much an art form. You know, every single person in the classroom could do their own post-tension design for that same slab and come up with a different result that all matches, that all works, right? So it's more of an art but because of that, you see a lot of iterations, and those iterations, every time you do an iteration, that takes a lot of time. So the more you can set yourself up to not do multiple iterations, the easier life's going to be, the less busy work you have to do. So let's jump right in. All right, very first thing, you have slab geometry. We need to figure out what the slab geometry and slab shapes are. And we talked about this some already, but where do you go? There's two really good manuals that are out there that I'd recommend if you guys get into this that your offices have. And one of them is the Good Guide for Design of Post-Tension Buildings, and the other is the Post-Tensioning Manual. These are both supplied by PTI, the Post-Tensioning Institute, which is recognized as the technical body of knowledge for post-tensioning. And both these documents have been extensively peer reviewed by multiple different engineers throughout within the industry itself. So if you have one of these, you have the first project, you got to figure out, okay, what type of slab am I even going to choose? We talked about two-way flat plate slabs, but there's a lot of different ones. There's column capitals, like we can see, let me get that stupid little pen back here. There's column caps right here. So remember, that gives you additional punching shear resistance. There's drop panels. We talked about that. This with a drop panel, if it's certain dimensions, that gives you flexural resistance and punching shear. There's slab with slab bands. So this kind of looks like a one-way slab system, but it's not. It's just thickening in your banded direction. It still behaves like a two-way slab system. And then there's waffle slabs. So just choosing the right system off the bat is going to make it so that you're not trying to push a square peg through a round hole later on and trying over and over to make a design work that doesn't want to make with the geometry. And this is a very, very simple step, but it's a step that gets screwed up a lot. So you go to these manuals I just showed you and you say, okay, I have columns spaced at 27 feet. It's a pretty square rectangular grid. Hey, typical span 27 to 30 feet. I can use this type of slab system right there. There's also the same for one-way slabs. You see this more in parking garages. Okay, I have ththese columns that are spaced. The architect wants them spaced at 65 feet in one direction this way, and I'm spaced in, we'll call it 25 feet in the other direction. It makes more sense to do it as a one-way slab. You can do slab and beam and girder systems. You see these in airport garages a lot. Pan deck systems, kind of like what you're seeing here. And there's a lot of comments of, hey, here's the amount of load that these slabs can take. 100 PSF plus if it's heavy storage. You start seeing these big research and development labs where you need these strong floors, you'll start seeing more of this waffle slab looking thing on there in the one-way direction. So this kind of gives you the starting point of, this is the type of slab I'm going to use with this loading on there. Then the second part is, okay, what's the depth? And we talked about this previously. We said for a two-way flat plate slab, the span to depth ratios are 40 to 45. And they say that in that, one of those books I was showing you guys. So you have that book open, you have confidence that you're choosing the right depth. From there, span to depth equals 40 to 45, depth equals span divided by somewhere between that 40 to 45 ratio. We can say our depth's equal to, if we have a 29-foot span, 29 times, inches to feet divided by 43, hey, it's an 8-inch deep slab. So we've, chosen the right slab type. And what I mean by that is two-way slab versus one-way, two-way with drop caps, panels, or whatever. We've chosen the correct slab type, and we've chosen the correct thickness. And that's extremely important, because if you don't, again, you're going to be fighting it. You're going to run into those. I've seen people try and make a 6-inch slab work and just boost up the P over A, the pre-compression, and they get to work, but it doesn't actually work from a long-term creep issues, because the P over A is 400 P over A or something along those lines. So right off the bat, it's a step that takes, the first time you do it might take you 20 minutes. After that, it takes you 5 minutes at most. And you're good to go. You have confidence that you're doing it right. All right. I'm going to skip this. This is a different slide, but all this is saying is, hey, here's sometimes if you have a slightly longer direction, the banded, you could do a thickening along your banded tendon lines, still have two-way slab behavior. Now you have to be very careful in the sizes that you use for that thickened element so that doesn't become a beam. And you could get a slightly longer, up to 40 feet in that particular direction on there. But in general, two-way slab, like I showed you back here, you're going around 30 feet roughly is kind of your upper limit of your spans on there. So, all right, easy. We know where our slab geometry is. We've gotten the project, we got awarded, we looked in our Revit model, we looked to see where the architect laid out the columns. Now we're able to tell the architect, all right, architect, you need an 8-inch thick slab and it's going to be two-way flat plate. You can go from there. So the next thing's called schematic narrative. And usually when you're starting a design, you do these, they're called SD narratives or schematic narratives. And lots of times they're just a piece of paper, a Word document that says, we expect the slab to be this many inches thick. We expect this many pounds per square foot of mild reinforcing. We expect this many pounds per square foot of steel reinforcement. We expect our columns to have 1% vertical reinforcing in there. We expect the ties to be on average number 4s at, call it 16 inches on center. And this is an early pricing document that you put together at that schematic level, which is the very, very first level of design. So you haven't started drawings, you haven't even done calcs yet, but somehow you haven't done calcs, but you need to be able to give them quantities of reinforcement early on. So it's a little bit of chicken and egg, right? So how do you come up with those quantities of reinforcement? Well, again, that guide for design and post-tension buildings, if you go in there, it's figured out for two-way flat plate slabs what those quantities of reinforcement are. So you don't actually have to go do any engineering calcs yet. You don't have to go spend 10 hours building a design just to tell them how many pounds per square foot of steel is going to be in there. You already know the slab thickness. We went over that in the first step. And so if we were to look at this and we're to look at that same slab example that we were talking about a little bit ago where we came up with the 8 inches thick, we can say, all right, it's 29 foot by 29 foot column grid. It's 8 inches thick. It's 5,000 PSI, very industry common PSI of concrete. I come to my directions here and you can see my bay in my one direction. They do increments of 28 to 30 feet. So I'm just going to round up to 30 feet right here. In my other direction, I'm just going to say I have equal spans. They're 29 feet. Again, I'm going to round up to 30 feet. It tells me my slab thickness needs to be 8 inches, but I already know that. It's just nice to have that validation that I'm doing it right. And then it tells me how much direction, how many pounds per square foot of reinforcement I'm going to have in the X direction right there in both post-tensioning and in reinforcing your mile bar. And when I say mile bar, I mean rebar, right? And then it sums it up at the very end, and that's what you see in yellow. And it says, hey, it's going to be 0.8 pounds per square foot of PT and 0.76 pounds per square foot of mild reinforcing. So you can go in and provide that to them. Now that's the minimum amount of mild reinforcing that we talked about from the standpoint of you just have a little bit of column head reinforcing on there. And that's also the minimum amount of PT. They're running like 125 PSI pre-compression on here probably. So it's not very much. So what I do is I take that number and I juice it up a little bit. Because I know it's based off 125 PSI, I'm going to juice it up. We know it's a linear relationship. I'm going to say I'm going to my classic 175. So I'm going to increase that 0.8 pounds per square foot PT reinforcement to 1.1. I'm going to increase my mild reinforcement because we talked about all that additional steel, the backup bar, the bar that's behind the PT tendon heads, the support steel. We didn't talk about this much, but all the diaphragm steel, you have drag bar dragging your lateral loads into your shear walls. You have diaphragm reinforcement for your cords for some tension in there. None of that steel's included in there. However, in that document, that guide document, based on my experience, we know in general that's going to come out to be somewhere around 0.5 pound per square foot. And just make it stupid clear when I'm saying per square foot, I'm saying square foot of slab surface area on there, right? So if you have a 30 foot by 30 foot bay, you take 30 feet by 30 feet, you have X amount of square feet there, you multiply it by your this pounds per square foot, and that's how much reinforcing is in that particular bay on it. And so I'm going to increase from 0.76 pounds of mild reinforcement. I'm going to throw another 0.5 pound in there just for all that miscellaneous steel. And I have what's highlighted in red. I have a schematic narrative right there. Again, the very first time you do this, might take you 20, 30 minutes of figuring out what pages to go to. After you've done it once, it takes you 5, maybe 10 minutes. The best part of this is I have a degree of confidence that when I do my final design, it's gonna be close to this, and they're not gonna come back and yell at me as the engineer saying, you told me it was only gonna be this much steel, and then your final design was this much, and you're saying, oh, sorry, I didn't know, I hadn't actually done the design, I was guessing. This gives you a degree of confidence. It also gives you something when you do your final design to back check on as an insanity check. If you're coming up with 3 pounds per square foot of PT reinforcement, you did something wrong, right? And so you know to go back and check on things globally. Again, if you're coming up with, call it 0.5 pound per square foot PT reinforcement, you did something wrong. So your end result should be somewhere close to this. Gives you a nice insanity check. Again, giving us confidence that we're doing it right. Okay. All right. So we got the architect. We told him it's an 8-inch thick slab. We feel good about that. We told them the pounds per square foot of mild reinforcement. We got that up to the contractor. We feel confident about that. Nobody's gonna come back and yell at us. So now it's time to actually really get into some of the thinking. And that's the topic of restraint to shortening. And we briefly touched on this last week, but restraint to shortening is that slab's gonna move. And it's concrete. Concrete shortens. And here's a picture. It's a real picture from a project in Denver that I worked on that you can see that little bit of this material right here. That's expansion joint material. Whenever you're pouring concrete up against a concrete vertical surface, if you're not actually hard tying into it, you put some expansion board right there. So that's about 1/2 inch thick expansion material. You can see that this is a 2-inch wide crack based on the tape measure right there. And really, if that was 1/2 inch board, that means that crack's opened up 1.5 inches. That's a lot of horizontal movement to be seeing with a concrete slab. And so that movement's very real. It's going to happen on your project, and you need to detail for it. This particular project, we had designed it so it would slip away from that wall, and we'd hard tied it in. We walked down the wall about 50 feet, and we saw a location where there just happened to be a little piece of rebar sticking out of the top of the wall right there that wasn't supposed to be there. And we had masonite in on the top, and that locked in this piece. And as that slab went to shoring up here, it cracked away, you know, this piece right there, just from that one little piece that locally restrained that slab on there. So I would say with post-tension design, more important than the engineering calculations that you guys are doing in that design example I gave you, what's more important is that you figure out this restraint to shortening and you figure out the right slab thickness at the very beginning. The software is going to do all those calculations for you. You're not getting fat finger number or anything. That's all being done in the software. It's more, have I engineered the theory of this concrete and the behavior correctly? And so this part is arguably one of the most important steps of your PT design. And I'd say the majority of lawsuits with concrete design with elevated post-tension slabs come from engineers who have not properly thought about this concept right here, this restraint to shortening. So, yeah.
Are you familiar with our parking garage? Didn't they have an issue with our parking garage in Bozeman here? Because that was like one of the first PT constructions in the area, and they didn't do that, and it did like pull away from the walls and crack and stuff. Are you familiar with that?
I heard rumblings about it, but I wasn't. I was never around when that parking garage. Okay. So I never actually firsthand saw it.
Okay.
However, so what we did at PTI is 2 years ago, we published a document that is totally focused on restraint cracks and their mitigation and unbonded post-tension structures. And again, you as an engineer, if you go to the building code, there's nothing in there about PT design. You open up, you see the 2 lines about post-tension, and you're kind of like, that's it. So you're left on using industry standard documents and design guides to follow. And the best part about following one is if you ever did run into legal issues or you did something, you're falling back on something that's been a peer-reviewed design guide from the organization that's recognized as the authority of being the industry expert on it, right? So there's a document out there that you can go to, and it goes all the way through this. We also did a webinar that you can go watch online about it. So here's some more issues. The majority of the time that you see slab shortening pop or rear its ugly head is going to be down at your foundation levels. I'm going to show you why that is here on the next slide. But you can see this is a different project where, again, the idea was we were going to do a slip connection with this foundation wall. This was 3 or 4 stories below grade. And it accidentally, the slip connection worked beautifully until right here, It accidentally got hard tied in because another little piece of rebar was sticking up out of that wall that wasn't supposed to be there. There's supposed to be a piece of masonite there to allow the wall to slip away, and it cracked locally right there. On the left-hand side, this is just another picture of that same exact behavior where it happened, where that slab's pulling up. So those forces that are going to develop of that slab shortening, they're massive forces if you have not restrained it on there. So let's talk about why we see that issue at the foundation level more than we see at the upper levels. If you were to look at this photo on the left, look at the very top two floors. If your slab moves in 3/4 of an inch on the top floor, well, your bottom floor is also moving, or the floor right below it, that's also moving in 3/4 of an inch. So it's moving together across there. You don't, you're not going to see a lot of cracking and major issues down there. However, once you get down to the foundation level, you're hard tied into the foundation, right? That's a fixed support from the standpoint of it ain't moving laterally. So if that can't move laterally, but the rest of your building up above is moving that 3/4 of an inch, this is where you're going to start to see those distress failures happen, because you've just now taken a concrete column and you've moved it 3/4 of an inch over. If you were to take a concrete column, model it in whatever FEA software you're using, force a 3/4 inch displacement on there, it takes a shitload of force to move a column 3/4 of an inch sideways. So if it's moving that much, there's going to be cracking happen. There's going to be a lot of nasty things happen there. So you got to figure out a way to detail for that. And you can see this picture on the left where you're going to see those cracks. It's going to act just like a moment frame. It's going to be restrained, and you're going to see this type of cracking that you'd expect to see in a large lateral event in these columns down at the foundation level. Same with your shear walls. Another thing to think about is if your building kind of steps out a little bit, right? We're going to have a ton of cracking happen right here, but then we have two different behaviors. We got a lot of behavior going on right here. Differential shortening happening from the slab below. The center of gravity of this slab's right here versus this slab's more like right here. A lot of different behavior going on. We're expecting to see some forces get developed in right there. So it's very, very common to see this behavior happen at the lower levels because the lower levels are restrained, but your upper levels typically are not restrained on there. Parking garages, Barry, you just brought the parking garage there. You see it a lot, especially with short columns. Short columns, there's no flexural, it's extremely rigid. It's not going to move sideways, right? It almost acts more like a corbel than it does a column right there from a lateral perspective. So if we have a parking garage, and oftentimes parking garages are one-way slabs, we have a ton of PT tendons going this way, and you can actually see the grout pockets from where all those PT tendons were right there. And then down below we have a beam, and we have a ton of PT tendons going this way. We got tug of war going on right here, and you can see those cracks happening. These are flexure cracks from all the shear in there that are happening there, and it's kind of hard to see there because this beam was restrained, but there's some also 45-degree cracks going in there. There's a ton of force going on there. So that's a poor design right there. They did not account for that horizontal shear that's going to be happening right there. Here's another kind of ramping column thing, and you can see almost a perfect, 45-degree crack going down, another one coming down. This beam is pushing this way. You got this beam pushing this way. It gave way. The left-hand side was stronger than the right-hand side. The whole thing tried to suck in. On the right-hand side, here's a concrete shear wall. Remember, I showed you that one example of, hey, our dream as an engineer is to have shear walls around the exterior of a building, but that's terrible when it comes from a pre-compression standpoint and a restraint standpoint. And you can see, look at how much shear has been dumped into this shear wall to actually get shear cracks in a member that's that thick. And that's where we have this slab kind of going this way, this slab, some sort of behavior like that. So these are other areas that you need to look out for. So look out at your foundations and look out at ramps. Those are two areas that will always bite you on there. So let's talk about that slab shortening. How do we actually go about and design it? And we're engineers. We need to put numbers to it just so that we can say we did our job. So let's put some numbers to it. ACI 209, that's a document on shortening that ACI has published. They have a method. The precasters, PCI has a method. There's a simplified method that you can use. You can also use FEA analysis and put a strain on everything and figure out how much that slab is going to move. It doesn't matter how in the weeds you get with these calcs and how many times you do these calcs, no matter what, you're always going to get the same answer, more or less. That slab is going to move 3/4 of an inch per 100 feet of unrestrained length that it has. I'm going to kind of really define what that is. If you remember one thing, remember concrete moves, especially post-tension concrete, it moves 3/4 of an inch per 100 feet of unrestrained. So if we have a 200-foot long slab, and let's say there's no shear walls, there's no external lateral restraints, it could be a slab on ground even. Say you put it on a frictionless surface and you pour this thing, this slab over time, it's going to shrink in 3/4 of an inch on either side, right? Because it's 200 feet long. So that means it's going to shrink towards its centroid of shape right there in plan view. It's going to shrink in 3/4 of an inch on either side. Now, in the 100-foot direction, it's going to shrink in 3/8 of an inch, right? Because it's 3/4 of an inch per 100 feet of unrestrained. So if you had a slab that was like this, and then let's say we had a really big shear wall on this end down here, and we had columns, 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 and let's just say this whole thing's 100 feet. Well, that shear wall now, this is a really rigid restraint. So because that's a really rigid restraint, even though it's only 100 feet long, in this particular situation, the whole slab is going to shrink in 3/4 of an inch for the left-hand side because it's going to shrink towards, it's actually going to shrink towards the center of its rigidity. Not the center of rigidity when you think of doing like rigid diaphragm analysis, but center of rigidity of like what's the most rigid element it's going to suck itself into there. And then if there are no rigid elements, it's going to suck itself into just the center of the shape, right? So pretty basic right here, but now we actually know a number that's going to shrink in 3/4 of an inch per 100 feet. So let's go prove this, that this is real. This was a 400-foot long slab in Denver, Colorado. It had a bunch of core walls in the middle of it, so everything was sucking in. This was, I think it was about 2 years after, a year and a half after this slab was poured. And you can see it sucked in 1.5 inches, which goes exactly on what I was saying, 3/4 of an inch per 100 feet of unrestrained. It was a 400-foot long slab, core walls in the center, so it really had 200 feet that was sucking in. It sucked in 1.5 inches, which was right what that 3/4 of an inch was that we were talking about in there. So that behavior, it's very real. It's notable behavior. If you don't design for it, it's gonna bite you in the ass. And a lot of people think though that behavior is only true with doing post-tension structures. So let's look at what percentage of that behavior comes from post-tensioning versus what comes from other factors in there.
Hey, Kyle, real quick.
Yeah.
Before you do that, if you go back to the previous slide. So we're okay having 1.5 inch gap on the edge there? Like, do you have to do anything with that? You just leave it sitting there? Do you cover it up? Like, what do you do with that?
So you got to figure out the engineer. Are you okay with having that? If this is 3 stories below ground, is this slab bracing my foundation wall? Is it a lateral brace for my foundation wall? Is it a giant retaining wall for the 3 stories below ground? If that pulls off, no, it's not anymore. What's going to happen is that whole the soil's going to push that wall into it anyways. Am I okay with it from the standpoint of maybe I was a smart engineer and I actually designed a column that was right here, that was underground, that poured up against my wall, but didn't actually hard tie to my wall. And so I do have a support right here, and it is pulling everything in. Sure, I'm okay with it. I got the gravity support, but what about the lateral support? And there's some tricks you can do with angles below, and I believe I might have a couple of those details. So, but you, I mean, that's a great question, Barry. You as the engineer, this is your responsibility to figure out if you're okay with this. And where everybody gets in trouble is when they don't figure out if they're okay with this, and all of a sudden that happens, or those cracks happen before, and then the lawyers start becoming involved. And then you're trying to defend yourself. And then if you didn't follow one of these industry standard documents, you don't have a leg to stand on. And then your professional liability insurance program's calling you up. And you're just not in a good position. And then you look like you graduated from the University of Colorado, not Montana State University.
Because do they ever ground it? Do they ever come back and fill it in with ground? Because I mean, after the shortenings happen, like,
Yeah.
Right?
So you can come fill it in with grout. They make, I spend a lot of time with the chemical guys from BASF and all those guys talking about what materials to fill, because they make some grouts that have some elasticity to it, so that the slab's always going to continue moving. If you grout it with something rigid, that's great, but then a new crack forms a month later.
Right.
on there. So yeah, you do come back with different things to fill it in.
Oh,
Sometimes if it's in a parking garage though, and you designed it to do this wall is self-supporting all the way up. You don't need it for lateral restraint. You're not dumping any shear load into it, and you got a column right where I drew that column. Yeah, you're fine with that gap.
Sure.
All right, so let's look at how much force is coming, how much this movement's coming from post tensioning versus how much is coming from other factors. And we can obviously see shrinkage is our biggest enemy when it comes to this. And shrinkage, that's shrinkage of the concrete. Shrinkage is moisture leaving the concrete. Again, it's just like you got a wet kitchen sponge, you leave for the weekend, you come back and that sponge is all dried and sucked up. That same behavior is what concrete's going through. As moisture leaves the slab, it's sucking in. And the majority of your shortening is going to happen with shrinkage. Well, that's a concrete material thing. So that doesn't care whether it's post-tensioned or whether it's mild. The majority of your shrink, if you have a mild slab, this same thing's going to happen. 60% is going to move from shrinkage. 18% is going to be from temperature. Again, doesn't care. So then you have 9% and 13% from elastic shortening and creep on this particular example. So that elastic shortening, that's that P over A that we talked about, right? You now put 175 PSI of pre-compression over there, you get that initial P over A. And then the creep, that's the, hey, we have a lot of force on a compression block. And I like to say creep's like that fat old guy who now he's 5'5" in his 80s, but back in his heyday, he was a big foot, right? Over time, that weight drug him down. That's the same concept with concrete. That's creep. It creeps it down. That compression block, it's moving under sustained loading, and you have a sustained 175 psi pre-compression over the cross section. Then you have even more on your compression block, right, from the flexure, and so then that compression block is giving you a little more deflection over time on there. So about 20% of that load is from, or of that shortening right here is actually from post-tensioning. The other 80% is from the concrete material itself. So it's a little bit of a myth that this amount of movement is coming from post-tensioning. Why you see it more with post-tensioning than you do with mild slabs, though, is with mild slabs, you have so much rebar in there that you get the same amount of shortening, but you get over a series of micro cracks, right? You might have, I'm going to butcher the math here, but you might have a bunch of 32nd inch wide cracks or smaller that equal 3/4 of an inch together. Versus with post tension, you just get that one big 3/4 inch crack on there. That rebar though hides all those micro cracks on it. So we got to put some numbers to this. We got to figure out how to design it, actually put some forces to it and figure it out. So this graph we're looking at, this is a graph of shrinkage and creep shortening on there, and this kind of more your long term. And you can see right around where the red is, right around 40 days, about half of that has happened already. So if we know it's sucking in 3/4 of an inch and right at 40 days, that means we know it's going to suck in roughly 3/8 of an inch over those first 40 days. And then we're going to have another 3/8 of an inch that we still have to deal with on there. In general, it's been empirically shown, when I say empirically, it means it's just been done over and over again, that if you can get the movement to be less than 1/4 of an inch per 100 feet long term after you lock everything together, you're not going to have big issues. So you kind of need to figure out, when am I going to actually hard tie that slab to that wall if I need it for some sort of diaphragm connection on there. And these graphs do a really good job of helping you try and figure out when that's going to happen. If you look at any shrinkage model, the majority of your shrinkage in concrete happens within those first few days. I mean, that's why curing concrete is so important to mitigate the shrinkage that's happening on there. And so, okay, we know the majority of that's going to happen right off the bat. So let's see how much we can let the slab move for the first X amount of days, a month, 2 months, 3 months on there. And there's a lot of different tricks that you can do that. You can do that by doing a pour strip right here, where you leave a 4-foot wide strip open and you let the slab move in. You can do that by doing permanent releases on your shear walls where it's always slipping. It's just kind of like a horizontal slip connection. You can do it while you temporary slip it, so you let it slip for the first 60 days, and then I hard tie it off after 60 days, and I'm going to get less than that quarter of an inch. That's where you as the engineer have to figure that out, use your art, use your judgment to figure out how do I make it so that this shortening, I'm mitigating the amount of shortening that's going to happen, and think about it. Another great example to look at too when we talk about the shortening is at what point do I just need an expansion joint because the slab's just too long. And this graph on the left is a really good graph because it kind of tells you, you know, if you have a pour strip, if you don't have a pour strip, are your columns fixed? We're usually more kind of like a fixed column behavior. What's our design temperature swing? You know, we're in Montana, so we get pretty high swings. Fixed columns. If I had a pour strip, you know, I might be kind of somewhere up here and say, all right, I could go about 300 feet in total length before I need to put a permanent expansion joint in the building and treat it like two separate buildings. If I didn't do that pour strip halfway through, oh shit, now I'm stuck around 200 feet of max length that I can do. So those pour strips help a lot because what that pour strip's going to do is it's going to allow you to suck in, you know, your 3/4 of an inch per 100 feet on each side for that first X amount of days. And then you go, once you pour that closure strip or that pour strip back in, now you've locked that slab in place. Now the thing's playing tug of war, but we've gotten it past that initial period of shortening, right? You can get real fancy with it. You can make yourself a finite element analysis model. And so you can see on the left, you can see these shear walls. Again, this is our dream when it comes to lateral analysis. We have awesome torsional restraint. We don't have any irregularities. We're not getting punished on any of those fronts. We got great resistance in both directions. Beautiful. It's our nightmare when it comes to post-tensioning because all our PT force is going to want to go in there. The model on the left, that's a finite element analysis model where they put strains of that shortening, surface strains on the slab and pushed on it. And you can see in the corners where those cracks are going to form right in here and right in here, which is exactly what this diagram has on the left-hand side where it's going to tear out unless we find a way to mimic that or to reduce it. And that could be by doing a pour strip in the middle. It could be by slipping these walls right here and allowing it to move sideways and then tying it off. So how do we do that? How do we make that happen? Well, here's some example details, right? Let's start with the one on the right. Here's a shear wall. If we smooth trowel the top and then we do an embed in the top and the bottom, we can come back and we can weld an angle in here. We got vertical bearing. Just from there, we don't have any shear resistance until we weld that angle in, but we can come in and weld that angle at some time. I'm going to put in my detail weld it 56 days after the slab's been poured. Then after it's been poured, now I have a way to get my horizontal forces from my diaphragm into my shear wall, right? They're going to come through this element right there. Another way to do it, say it was just a bearing wall, you could do a corrugated sleeve through that rebar and leave it open. Now the whole slab can move back and forth. It's not catching on that rebar, and you're good there. Another option is you can do that corrugated sleeve, and then after a certain amount of days, come back and fill it in with grout, and then pour the wall on top. That's going to give you that initial release to get the pre-compression shortening out of the way. And if you wait for 3 to 7 days, you're going to get some of that initial shortening out of the way from shrinkage. And then you come back and you put some grout in there. So that's another detail in there. This one on the left, that's what I was talking about with, hey, we have a foundation wall below ground. We still need that vertical support. Instead of trying to support that slab off that retaining wall below ground, pour a column, a 3-sided column up against that wall. Pour the wall first, pour a 3-sided column up against it, put a piece of masonite or slip material in here. Now this column, you know, it can pull away from the slab right there, right? So that's a really good way for us to try and support the slab vertically, but not hard tie it in that wall. We all just saw what happens when you try and hard tie that thing into the wall. The thing cracks and looks terrible, and everybody's calling you out. Another option is, all right, we feel good about long-term restraining into the wall. What we'll do is we'll pour this slab up to right here and we'll put some formwork. We'll keep our formwork in place. We'll wait till 28 days have gone by, and then we'll come in and we'll pour this last 4-foot section. And one, this gives me the ability, if you're doing this below grade, you have to do it anyways, because below grade, you have the retaining wall. You still need access to stress those tendons. So at least on your live end side, you still got to do this detail just to be able to stress those tendons in there. But you could do this all the way around on there, keep your formwork in. After the slab's gone through that initial shortening period, you come back, you pour that 4-foot section. Now I got my vertical support, I got my flexural support at the end, I can rip my formwork out. Now I'm hard tied in though, so I better be damn sure that whatever movement, once I tie that thing in, I have enough rebar in there to prevent those cracks. What I'll do on a subterranean garage like this is I'll just put in a very light mat of number 4s at 24-36 bottom, just to help with some of that crack control, because I know long term I'm still going to get that, and I'm fully restrained all the way around the perimeter on there. There's other details you could do at the top of a foundation wall. You know, you could stick a piece of rebar out here. You could stick a piece of rebar out here. You come back, you could pour a curb. You could do a thing where you have just a little 2-inch bearing and you just kind of notch it right over. You don't need a ton of bearing with the wall. And then you come back and you pour this wall later at another day. You know, that alleviates that temporary support. But in general, what you're trying to do is you're trying to do what's shown on the left-hand picture. You're trying to put in masonite down here, so thing can move. You're trying to put in that rigid insulation that you need to chip out, and that's the lesson learned that we showed previously on the right. If you don't do that, rigid insulation's rigid, and it's going to crack, and you're going to get that shear key on there. But this is the type of detail you're going to do with this particular one. You know, we eventually stuck rebar out here. We came back and we poured in it looks like the wall kept going up on this one. So this detail was more or less what we're staring at on the right hand side right there. That's that detail. Whoops. That's that detail in real life right there. It's partially supported by this thick foundation wall. This is a pretty thick wall. This thing looks like it's almost 2 feet thick or 18 inches. So this must have been one of those like 4 stories below grade structures. But we're also going to look for things like this pilaster that's going to turn into a column that's going to become an accidental shear key, and we're going to put an intentional gap around there with some foam, and then we're going to chip that foam out before we stress the deck on there. Other things that we can do is we can put in some supplemental rebar to help that crack control. I talked about with the mild slabs, that same amount of shortening is happening. You just have rebar that's preventing it from cracking as much. So let's look at core wall, right? This is from my finite element model. They went above and beyond and made this fancy ability to view where all your rebar and tendons are. The tendons are in red. This is a concrete core wall right here for the stair shaft. Well, I know I have a big lateral element here. This lateral element's going to suck up all my pre-compression as a shear wall, so I'm not going to have any pre-compression kind of in this region. If I don't have any pre-compression, I really don't have any temperature and shrinkage crack control in there. So what am I going to do? I'm going to throw a couple pieces of rebar alongside that concrete core wall right there to make sure that that happens. And I learned this lesson the hard way. We were doing a building multiple stories underground, and it was up on like, I don't know, level 5 or level 6. Somebody was moving in with a U-Haul, knocked the sprinkler head, and started flooding this region right here. Well, this crack, we didn't have this bar in here, so we had pretty good crack right here. And it happened at every single level for the next 5 levels going all the way down. Well, the base level, they reserved this parking right here for the rich people because it was right next to the stair cores, the VIP parking. So there's all these like $150,000 vehicles right here. Just got soaked and stained with all kinds of concrete stuff that came down because that sprinkler head cracked 5 levels up above, or broke off, started flooding that level, and that crack was on all 5 levels, and then the water went all the way down, picked up all the concrete dust and everything all the way down. So that was hey, lesson learned from the field. I should probably put some reinforcing right here. There's a crack that's going to happen. If I were to look at my FE8 model and look at my pre-compression, I would have seen I got no pre-compression right there. I got to do something about that. But I didn't back then. That's what happened. All right, now we have 2 concrete cores. Maybe I'll do a pour strip between them like this, so they're not playing tug of war on each other. But eventually, once I place that pour strip back, they're going to be playing tug of war on each other as that slab shrinks, right? It's going to be shrinking in. It's going to be shrinking into its center of area. It's going to want to form some cracks in here. So what am I going to do? I'm going to put a couple horizontal pieces of rebar in there. I'm not going to do any math behind it. I've already said I'm going to lock this thing off after I know the shrinkage is less than 1/4 of an inch per 100 feet. So I've already figured out that math. I detailed it properly by putting in this pour strip, or maybe I did that slip connection that I was showing you on the top of the walls with that angle remember, we'll go back. That detail, maybe I did that detail on one of the cores. So this one is a temporary, this one's a temporary release, and then eventually I weld it off. But I've used my creativity. I figured out a way to get that initial shortening out of the way. I still know there's a 1/4 of an inch per 100 feet of strain that's going to happen. So I'm going to put a couple pieces of rebar in right there to mitigate that strain on there. So, all right, that's a lot of information. How do we go about this? What are the steps we follow to do this? And again, this is one of the most important steps to follow, and this is where most people screw it up. And I'd say even 80% of engineers that do post-tension design don't do this, and they run into issues. First one is, we saw the majority of the shrinkage is going to happen from our concrete mix design. So let's have a good concrete mix design. I specified that my concrete cannot shrink more than 0.04% on a 28-day shrinkage test per some ASTM number that was designated for doing this measurement on there, right? And they achieved that by using certain size aggregates, certain large cement ratios, and sometimes some additional admixtures in there. But I spec as a performance spec. I don't tell them your concrete mix design needs to be this, this, and this. I just say, I don't care how you get there. You just got to give me concrete that's less than 0.04% at 28 days. So right off the bat, I've controlled I'm going to have good shrinkage behavior of my shortening behavior of my material. And I know the biggest culprit out there is the concrete itself. Second one is that PDF. Remember I said earlier, print out a PDF and look at where everything is. I've now gone through that PDF and I've identified where are my lateral restraints, shear walls, those short columns, foundation walls, infill walls. Maybe I put a CMU wall in there that I didn't think was going to be a lateral restraint. It was just a firewall. Oops, it tied in. You know, I go and identify those. I go and identify, do I need pour strips or stressing strips based on how long the slab is? You know, I showed you guys that graph of here's how long you can go without expansion joint. Here's how long you can go without doing a pour strip. I've kind of figured that out. Now I'm numerically going to predict how much the slab is going to shorten. I'm just going to do 3/4 of an inch per 100 feet. I'm going to say it's going to shrink into the middle, 400-foot long slab. That thing's going to suck in 1.5 inches on each side there. I'm going to figure out how I'm going to look at some of those curves and be like, all right, how many days is it going to take until that shortening is down to less than 1/4 of an inch of long term on there. And then once I've kind of figured out all that, I'm going to go element by element and be like, how am I going to detail this particular one to resist that shortening? Maybe on those short columns, I have no choice. So I'm just going to put an ungodly amount of ties in there. I'm going to treat it like a moment frame. So I'm just going to make it so it's a ductile member and say, hey, it's still going to crack, but I put enough steel that it's got some ductility and it's going to be fine on there. Maybe other ones, I'm going to say I'm going to do that short term on there. And then the short term release, I'm going to tie it off after 28 days. You know, that's where you as an engineer are going to use your thinking to think right. At the very end, I'm going to look at, okay, after I've hard tied it off, I know I'm going to have some sort of supplemental model reinforcement in there because I'm still going to have movement. Where do I want to strategically sprinkle a little bit of rebar to do a little bit of crack control so I look good? So, all right. On Friday, we'll get into the rest of it, which is going to go a lot quicker than that topic. That topic's just a important one, so we spent some time on it. All righty, guys.
Cool. Thanks, Kyle.
Cool. Have a good one. Talk to you guys on Friday.
Your classmates suggested that.